This video introduces the topic of finding real and complex zeros as well as graphing polynomials. The learning outcomes are to use definitions of zeros, turning points, and end behavior to describe polynomial graphs. To find all real and complex roots of a polynomial by using the conjugate zeros theorem, the fundamental theorem of algebra, and the intermediate theorem, as well as the previously covered theorems. And finally, to use this information to graph polynomials. Before we begin graphing polynomial functions, let's take a look at some simple polynomial functions and check out their end behavior. In the My Notes for this assignment, we have the following graphs: linear, cubic, and to the fifth power. Notice that each of these parent functions has the domain from negative infinity to positive infinity, and their end behaviors are the same. As x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. If there had been a negative leading coefficient, the end behaviors would change, as does the graph. So that as x approaches negative infinity, the y values will actually approach positive infinity. Another thing I want to mention about these odd functions is that there will be at least one zero for these polynomials, since we see that on one end of the y values are negative and on the other end the y values are positive. So somewhere the y value was 0. So there has to be at least one zero in any odd-powered polynomial. The next set of graphs are those of even powers, quadratic, to the fourth power, and to the sixth power. Notice that each of these parent functions have the same domain from negative infinity to positive infinity, and their end behaviors are the same. As x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y also approaches positive infinity. If there had been a negative leading coefficient, the end behaviors would have changed, as does the graph. So that as x approaches negative infinity, the y values would approach negative infinity, and as the x values approach positive infinity, the y values would approach negative infinity. Notice that there is no guarantee that there will be at least one zero, since the ends are not going in opposite directions. This is what the intermediate theorem says, that if a y value is positive and another y value is negative, then there has to be at least one zero between the corresponding x values. This is not the case for these even powers. Let's take a look at more complicated odd-powered polynomials. There are no complicated linear functions, so let's move on to the cubic function. The simple version is x cubed, and we see that it has exactly one zero. And we see that the graph curves through the x-axis. This curve through the x-axis means that the polynomial has one factor that is raised to the third power. So for example, we can graph y is equal to the quantity of x minus 2 cubed by using our transformation knowledge. That means it's translated 2 units to the right. And note that x is equal to 2 is the only zero for this graph. A more complicated cubic function would have an x squared term as well as an x term, and maybe even a constant. And the number of zeros can change from only one zero to 2 zeros, or even up to 3 zeros, as shown by these graphs. Similarly, we can do the same for x to the fifth function, and see that we can have 1, 2, 3, 4, or 5 zeros. These places where the graph is tangent or just touching the x-axis are caused by an even multiplicity of zeros or roots. This means that the polynomial has a factor that is squared or to the fourth power. Our conclusion is that odd-power polynomials with power of n can have 1, 2, 3, all the way up to n zeros. And this is backed by the fundamental theorem of algebra that states that a polynomial function will have at most n number of distinct zeros, if n is its highest power. Now let's look at more complicated even polynomials. For the quadratic function, we see that it can never touch the x-axis, or maybe just touch the x-axis, or it may have two x-intercepts. So we see that even functions can have 0, such as x squared plus 4, or 0, such as the quantity of x minus 4 squared, or 2 zeros, as in x squared minus 4. We can do the same for x to the 4th function and find 0, 1, 2, 3, or 4 zeros. Our conclusion is that even-powered polynomials with the power of n can have 0, 1, 2, 3, all the way up to n number of zeros. And this again is backed by the fundamental theorem of algebra. Again, I want to remind you what happens graphically when we see factors raised to exponents. So for example, if we have p to the x is equal to negative parentheses x minus 2 times parentheses of x minus 3 squared times x minus 4 cubed, we should see that this is a polynomial of degree or highest exponent of 6. If we were to multiply this out, we would have x from the first factor, x squared from the second parentheses, and x cubed from the last parentheses. And when we multiply x times x squared times x to the third, we get x to the 6th. From the exponents on the parentheses, we know that the graph will go through the x-axis at x is equal to. The graph will only touch the x-axis at x is equal to 3. We see this from the square power on the x minus 3 factor. And finally, the graph will curve through the x-axis at x is equal to 4. Because this is an even-powered polynomial and the leading coefficient is negative, we know that the end behaviors will both be going down.